What other questions might this raise? We were able to pull it off a piece of tape, and let's do it real quick. So we pulled it off a surface, and we saw electrical interactions. So what other questions come to mind here that we might be interested in? Does anything happen to the surface? Okay, so surface interactions. Surface interactions might be important because it looks like one surface is in contact with another, right? And if I pull one tape off another, or if I don't pull it off the entire desk at all, but clearly there's a sticky side, right? We're pulling off one sticky side off another, and somehow this leads to a charge, right? So maybe the surface interactions, something's going on with the surface here, and more generally, maybe contact interactions. And maybe thinking about those things might be important for figuring out why does the tape charge up? What's the mechanism behind, or why does the tape get a charge? And just generally speaking, why can we have a neutral object and then some contact interaction occurs and suddenly it has a net charge on it? Any guesses? Just what might be happening at the surface? Okay, there's friction. What would that have to do? Or what we end up with what? We end up with a tape that has what? A net charge, which means there's what? Okay, there's a disbalance of electrons relative to protons, right? We either have too few electrons, meaning we have an excess positive charge, or too many electrons, which means we have an excess negative charge. How might that happen? Okay, so one possibility is you left electrons behind, or maybe you pulled electrons off of another surface, right? Is this possible? Could we pull protons out of the nucleus of an atom and have more protons? I see people shaking their heads. That seems really unlikely, right? I mean, the protons are really bound very strongly to the nucleus. You'd need a nuclear interaction, right, or a strong force interaction to pull protons out of the nucleus, and I don't think that's happening with these tapes. So it's probably something having to do with the electrons. It might be a little bit more complicated than that, but we'll come back to that. What other things could we think about? Any other? Okay, how much charge is there? Yeah. Did you mean how much, or what's the sign? Or what's the sign? Okay, so what's the sign? And the sign, we talked a little bit last time. I couldn't quite get it to work, but if you knew from experiment some object that charged a particular way, say positive, then how would you test that something else has the same charge? You look for repulsion, right? You look for repulsion. That's the key idea. Attraction is not necessarily conclusive because you can have attraction between positive and neutral, or charged and neutral objects, okay? But how much charge is another, more quantifying this, how much charge is another question, and this is something you'll be doing in lab, trying to come up with a way to at least get an order of magnitude estimate for how much charge there is. Okay. Anything else? Any other questions? Those are kind of the big ones, and so maybe we'll go with those for now. Yes? Static electricity. So what we are actually dealing with now is what's commonly termed static electricity. Okay. Oops, lost my microphone. Static electricity is a term that you hear kind of a lot in sort of everyday parlance, everyday life. When a physicist says static electricity or static electric interactions, he just means the type of electric interactions we've been dealing with so far, meaning charges that are stationary, charges that aren't moving. So pretty much everything we've been talking about is really a form of static electricity in some sense, okay, as opposed to the dynamics of electric interactions when charges are actually moving in circuits, for example, or when we're dealing with magnetic interactions, we'll later see that those are due to moving charges. So when you hear static electricity, it's really nothing different than what we've been talking about so far. Okay. Okay, other questions? That's a good question. All right. Today we're going to distinguish between electric interactions in two different types of materials. We're going to define and talk about conductors versus insulators. And simple definition, basic difference between the two is that a conductor has mobile charges that are free to move. Hence the name mobile, just to drive it home, that are free to move throughout the material. And insulators don't. That's basically it. Insulators don't have mobile charges. Okay. So what we've been dealing with so far, the case of the tape, for example, was an insulator. Insulators, we have charges. We have positively charged nuclei and electrons bound to those nuclei. But the key idea is that those electrons are bound to the individual nuclei and can't move, at least not very much. Okay, they can shift a little bit. The electron clouds in the atoms or molecules can shift a little bit, but they're not free to move throughout the material. Okay, so when you're looking at an insulator that's polarized, so here is some block of an insulator. What's an insulator? Examples of insulators. What kind of materials are insulators? Wood, plastic, rubber is an insulator. Okay, a lot of organic materials, right? A lot of things having like hydrocarbons in them are insulators. So let's say we have a block of plastic and we bring a positive charge nearby. It's a neutral piece of plastic, and my markers are dying a little bit here, so let me grab another. And it polarizes, and the way we said we indicate the polarization is that we can think about the individual molecules actually becoming induced dipoles. Okay, and if I were to draw, in fact, this is a point charge. If I were to draw the electric field due to that point charge, it's kind of pointing away like that, right? So to make it is to give the sense that this is polarization due to this electric field. I'm even drawing the dipoles kind of lined up in the direction of the electric field. And if you wanted to indicate, since the polarization or the dipole moment is proportional to the field, if the field drops off with distance, we can kind of draw a less elongated dipole farther away to indicate it's not quite as polarized. But the key idea in the way to represent this in sort of this cartoonish way is that you're drawing the individual molecules and showing a polarization for each molecule or for each atom. Okay, so each individual atom becomes polarized, or it becomes an induced dipole, and so the whole material is polarized. But the atoms or the electrons still stick with the nuclei. The electrons are not free to move around the entire material. Okay, so that's a polarized insulator. And of course, with the tape, we saw a case of where we had excess or net charge on an insulator. And the key idea here is that if you're able to place a net charge or an excess charge on an insulator, excess charge tends to just stay put. Okay, so let me write it that way. What do I mean by that? Well, I could do this. Let's say I have this little piece of plastic, like lucite or Lexan or something like that. And I'll do another contact interaction, another surface interaction, and charge up, put an excess charge on the piece of plastic by rubbing it with some silk. And I'll just rub one end. And it will turn out that the charge, if there's any charge at all, will just stay where I placed it, where the contact interaction occurred. It'll just stick there. It won't spread throughout the entire material. And I can again show that if I charge this end with the same material, give it the same charge. So if I bring the two charged ends together, I should see a repulsion, maybe. And I do. That's satisfying. So we see these two charged ends repelling. If I brought this end to that end, what should I see? Yeah, I should see an attraction, right? Now, it might be a little hard to see because there's kind of a lot of friction on this little pivot here. But if I bring a neutral end to the charged end, I got to get close. Oh, yeah. I can. It's starting to go. Oh, that's pretty nice. Yeah, almost. Okay, it almost works, right? It's just a lot of friction on that pivot. If I bring the neutral end to this neutral end, I should see nothing at all. Okay. So the key idea here is the charge stays put. It stays where I placed it. I rubbed this end. You didn't see the charge spread throughout the entire object and charge up the entire rod. If you had, I would have seen a repulsion between these ends, right? So insulators, the charge tends to stay put. And because of that, why does that happen? Well, because there are no mobile charges. You stick excess charge in one place. There's no mechanism by which it can move throughout the entire material. You can place excess charge on the surface, which is easiest to do with these sort of surface interactions, or in the interior. Now, it's kind of difficult in practice to place excess charge in the interior of an insulator. But one way I could do it, for example, is if I had one surface that I charged up, one surface of an insulator I charged up, and I just glue it to another insulator, okay, just stick them together with some glue, and now I've got some excess charge in the interior, and it will just kind of happily stay there because there are no mobile charges for it to move around, okay? So charging in the interior is okay, charge on the surface is okay, and it just kind of stays put where you place it. As opposed to a conductor. Give me an example of a conductor. Metals are conductors. Anything else? There are other. Yeah, water, and particularly water with ions dissolved in it, right? So aqueous solutions, let's put it that way. And let's just look at an example of a conductor. Let's say we have some salt water. So here is, say, a beaker of water, and I've dissolved some ions in it. So if I dissolve salt in it, the ionic bond in the salt molecules breaks apart, and so you end up with positively charged sodium ions and negatively charged chloride ions just kind of all floating free. Now, of course, this is a huge exaggeration here. But you get the idea. These ions are free to float about throughout the entire aqueous solution, and so these are the mobile charges. Okay. They're free to move about, free to float throughout the entire material. Okay. Another example is a metal. And metals are kind of special, and they're going to be extremely important in this course. We're going to be talking about the properties of metals over and over again. In those of you who took 205M probably remember the ball and spring model of a solid, where we thought about the structure, the internal structure of a solid, as behaving as if it were hard spheres connected to each other by spring-like forces. Okay, and so the hard spheres essentially were the atoms, and these were the interatomic bonds. Okay, and this model is sometimes called the lattice. Okay, meaning the structure of the atoms inside the material. We're going to add on to our model of metals, of the internal structure of metals, by saying not only is there the atoms and the interatomic bonds, which are essentially the inner electrons that are bound to each other, and these interatomic bonds are essentially the electrons that are bound to the atom. Okay, but metals are kind of special in that they also give up at least one electron that is free to move about the entire object. Okay, so if I have a series of atoms in a lattice in a metal, this atom gives up an electron, and now it has a nucleus plus a smaller number of electrons, so it actually has a positive charge now. And this atom gives up an electron, and this atom gives up an electron, and this atom gives up an electron, and this atom gives up an electron. Where do those electrons go? They go into what's called an electron sea. So here is our block of metal. You can think of this as an electron sea, a sort of free-floating ocean of electrons that are delocalized. They're not bound to any one particular atom. They're just kind of floating, in a sense, throughout the entire material, and they're free to move about. So you can think of the electrons almost like a gas, where electrons are free to bounce around, jiggle around, move from one side to the other without anything impeding them. Okay, at least as a first approximation. And we'll just kind of take this as our model of how things behave. For an explanation of why this is, you need quantum mechanics to fully explain this. But one way you can picture this, and I'll show a little VPython program. So here's a model of a metal, okay, and you can see a series of positives, and those are what are called the atomic cores, or sometimes the ionic cores, because they are now ions. They have a single positive charge, which consists of the nucleus plus inner bound electrons. So those atomic cores are just sitting there, but each atomic core gives up a negative charge. It gives up a single electron. And those negative charges are free to kind of float about. You can think of this as electron C as being able to shift one way or the other, while the interior still stays neutral, because for every ionic core, there's a electron. Okay, so you can think of sort of the electrons as being superimposed over top the atomic cores, and the interior still stays neutral. But if you have a case of polarization, let's say you bring a positive charge near a conductor, near a metal. Here's a positive charge, and here's a block of metal. Well, the electric field due to this positive charge is pointing that way. So we can think of this as the applied electric field. How do I draw the polarization? Well, the interior stays neutral. What happens is the mobile charges shift. Okay, so the electron C shifts a little bit. You can think of the applied electric field as exerting a force on the individual electrons, causing them to, entire electron C to migrate from one side, migrate a little bit. So you can think of it as the electron C kind of sticks out a little bit on one side. Okay, there's a greater probability of finding electrons a little bit out of the surface, okay, in some sense. And that leads to an excess negative charge on that side. And if their electron C is shifted that way, you're going to have an excess positive charge on that side, okay? So that's the basic idea, okay? Mobile charges inside, and this has a number of different consequences. One is, again, polarization is a shifting of the mobile charges. In this case, the electron C, if you're talking about a metal. Excess charge, well, think about if I tried to charge up a piece of metal or a conductor. If I placed any excess charge in the interior, say somehow I was able to inject some negative charge in the interior, those charges in the interior are free to move about. If I have a concentration of negative charge in the interior, what's it going to do? It's going to pull positive charges in. Well, the positive charges are the atomic cores, right? They're pretty much static because they're made up of the nuclei, and the nuclei are really heavy, and so there really isn't anywhere for them to go, or they can't be really pulled that much. Yeah, Luke. Okay, so the electrons on the outside will be repelled. So let's think of it this way. Here's an electron. It's next to a whole bunch of other electrons. It's going to experience what type of force? It's going to be pushed in what direction? Kind of outward, right? So that electron gets pushed outward. Here's another excess electron that's near a whole bunch of excess electrons. It gets pushed outward. So the end result is that when everything settles down, the excess charge is only going to be on the surface. So for a metal, excess charge can't be in the interior. It can only be on the surface. And even on the surface, it tends to spread out. Okay? If I tried to place, even if it were on the surface, if I tried to place some excess electrons on this piece of metal, just at this location, well, again, we have the same problem, right? The electrons are going to be repelling each other. They're free to move about throughout the entire material. And so you'll see after a short amount of time, a nanosecond, very split second, the electrons will try to spread out as much as possible over the entire surface. So you can't just place excess charge on one little patch like you could with the insulator. It tends to spread out over the entire material. Okay. We can quantify this a little bit by actually being a bit more precise about our model of a metal,